This video we will use series sum and LINEST polynomial regression to generate the coefficient, the expansion coefficient of NORMDIST, the normal cumulative distribution function. And we will also use the LINEST to generate the coefficients of regression, the regression coefficient to the polynomial degree 8. So we will start with the NORMDIST of the x values, and the mean is 0, 1 for the standard coefficient, and 1 because it is normal cumulative distribution function. So, and it has to be an array formula, so we will use array formula. So here we have the normal distribution trend line. This is the cumulative distribution function trend line, where you have the values of B0, B1, B2 up to B8. We'll calculate these values using LINEST. The normal distribution function can be expressed in the form of Gauss function and ERF function. Let's begin with the ERF function. This is equal to ERF, array formula, ERF for the values of x. So this is the ERF function. We convert it to the Gauss function. To convert that, you have to factor in square root of 2 within the x and multiply 0.5 onto ERF. So we start with the square root of 2. We just factor in square root of 2 and we multiply 0.5. So we have a difference. They are not parallel. There's a difference of 0.5. So that is the Gauss. The red one is the Gauss function. We add 0.5 to the Gauss. So 0.5 plus. Now we have all values are exactly the same. This is the norm distribution in terms of the error function. So that is the expressed in the error function. The error function can be expanded using Taylor and Maclaurin series distribution. Maclaurin series. So we have the formula of error function equals 2 times square root of pi, 2 over square root of pi times the coefficient times x to the power 2n plus 1. The summation of the coefficient times 2x x to the power 2n plus 1. The coefficient will be in the form of negative 1 to the power n over factorial n times 2n plus 1. So we begin with the factorial of the denominator, where our n starts from 0 to infinity. In this case, we will be limited to the data set range. So let's calculate the coefficient. We begin with the denominator. Our formula, 1 over factorial n. That's the factorial part. Now we add 2n plus 1. 2 times n plus 1. So we have the denominator part. Now the numerator. It will be negative 1 to the power n. Now we have alternating signs of negative 1. So we will use this coefficient to calculate for the ERF. Start with RA formula, ERF, series sum of the values of x, where the starting power will be 2n plus 1. So x to the 2 times 0 plus 1, so 1, that's the starting power. And the increment, so the next is 1, n equals 1, so 2 times 1 plus 1 is 3. So between 1, 3 and 1, so that the increment is 2. And the coefficient will be this range. Next, we factor in, to complete the Gauss function, we factor in the square root of 2, or DRF, we add 2 pi, factor in 2 pi. So 2 over square root of pi, not 2 pi, but 2 over square root of pi. 2 over square root of pi. So that's the ERF function. That's Now that we've done with the ERF function, we change that to Gauss by multiplying zero point 0.5 and factor in square root of 2. So first we factor in square root of 2. That's divided by square root of 2. Now that we're done with the square root of 2, we multiply 0.5 to the series sum. So that's 0.5. Now that we have this is now the Gauss function, where they are parallel, the difference is 0.5. To make this equal to NORMDIST, you add zero point 0.5 to the Gauss function. So add 0.5 to the Gauss function. So 0.5 plus. Okay, so we now have all three, all in the same line. The values vary slightly. There's just, but they are the same, exactly the same in the areas close to zero. They're just the same in areas close to zero, but as they go farther from zero, the value, there's a bit of an error. But this is a very good approximation. So we will calculate this uh, regression coefficients, because these are polynomial regression to the 8th degree, using LINEST. So we'll expand this, we'll move this, and transfer this to the top for comparison. So our legend will be on top. So we can compare we can match our calculations of the LINEST coefficient, or the coefficient of regression. So to do that, to calculate for B0, B1, B2, and B3 using LINEST, we have to complete the 1 comma x matrix. So we begin with the function. So we fill in the 1 column, the x column, x squared column, x cubed, and so on. So we start with with the power, which is transpose of the range. Now that we have the one power, we can now complete the 1 comma x matrix, which is RA formula of these values raised to the power 0. That's for the 1 column. And we drag this to the right to copy the formula. So we have the 1 column, then the x column, which matches to our x values. Then we have the x squared column, x cubed column, x to the 4th column, x to the 5th column, x to the 6th column, x to the 7th column, and x to the 8th column. Now we can calculate the LINEST. The LINEST for this range, and the expansion. We start with the LINEST of the expansion. LINEST of the NORMDIST itself, the function itself. So our values for B 0.5, B1 is 0.399, B2 is 0 because this is 4 times 10 to the minus 23. That's already 0. B3 is 0.065, negative 0.065, which is also negative 0.065. B4 is 0. B4 is 2 times 2.08 times 10 to the minus 22. That's very small, so it's already 0. And B5 is 8.79 times 10 to the minus 3. It's matched. And B6, our B6 is 2 times 10 to the minus 22. That's already 0. And B7, negative 5.98 times 10 to the minus 4, which matches, which is a good match. And B8 is negative 3.17 times 10 to the minus 23. That's already 0. So this is the LINEST output of our NORMDIST. Now we begin with the LINEST output of our calculation using Gauss or the ERF function in terms of the ERF function. So this is equal to array formula or LINEST of these values and the x values. So we have the same values of the coefficients B1, B0, B1, B2, they're the same. Then let's try this, the third one, this range. So this will be LINEST of these values of our expansion and this range. Still, we get the same values exactly except for the last digits, but they are exactly the same. This completes the normal cumulative distribution function regress to the 8th degree linear with using linear polynomial regression and Taylor-Maclaurin series expansion using SERIESSUM.